So, hello again, everyone. This class will be about analogical classification, which is a topic on which I've worked quite a bit, and which I think it's very interesting. One thing to keep in mind is that it is a really big topic. There's a lot about it, even though it's not very well known among linguists. So what I'm going to do for this class is just give you a brief overview of what analogical classification is about, try to contextualize it, and present to you a couple of small case studies which I think are interesting and which maybe give you some inspiration for your projects or for your work later on during your studies. So I usually like to start talks on analogical classification with this quote, because I think it's a quote which encompasses everything that analogical classification is not. So Dichellieu and Williams basically claim that the lexicon is unorganized and just has randomness and lawlessness, as they call it. The view from an usage base or from this perspective is that the lexicon is the opposite. The lexicon is highly structured and highly organized, and this structure part of the structure is what allows us to do analogical classification. So one point to keep in mind when one talks about analogy is that there are many different things and many different fields where the word analogy is used. And in linguistics also, we have analogy in language acquisition, in the creation of neologisms, in something that's called paradigm unity as a force of language change. And what interests us is structural and functional similarity. So to give you just two quick examples of some of different kinds of analogies, there's something which is quite pervasive and which in my experience is what people mean when they say analogy is single case analogy, and this is unsystematic analogy or an unsystematic relation between two items, and it usually happens for the creation of neologisms. Here I have a couple of examples in Spanish, but I think that French does exactly the same thing. So you have the old verb aterrizar, which is to land, and people have analyzed it as being composed of the terra, which means earth, part here, or stem, and by analogy to this verb they've created alunizar, which is to land on the moon, and which contains luna or lun instead of terra, which means moon. So this is a case of single case analogy because there is no systematically productive process by which you can derive new nouns doing this. This is fairly single case. I think it also works for Mars, but nothing else. That's basically it. And this is what you will often see as analogy. So this was derived by analogy. So by making reference to a previously existing item, you create a new item without using any systematically productive morphological process. Now, a very different kind of analogy, also very interesting but quite different, is proportional analogy, also called fourth part analogy, which works more or less as follows. The idea is that you have a proportion with four parts, in this case A, B, C, X, and you can say that A is to B like C is to X. And the idea here is that you know A, B, and C, and from the relation between A and B, and from knowing C, then you can derive X. It could be any of this four which is unknown, as long as you know three of the parts of the proportion, you can derive the missing one. As an example, imagine you have the Russian noun shkola, which means school, in the nominative. That's shkola, and you know that the accusative is szkolu. Now, if you're presented with the word for man, mushina, then you can fairly easily guess that the accusative of mushina must be mushinu. And that's fine. So that's proportional analogy. This is probably the oldest type of analogy that's been studied. It was discovered by Aristotle like 2000 years ago, so it has quite some history. It was ignored in linguistics during some time, but it's been making a comeback recently. And finally, we have analogical classification, and this is what I am going to be talking about in the lecture today. Now, the best summary of what analogical classification is the statement that objects that behave the same or behave alike must look the same or must look alike. And here with behave, we mean basically anything. It can be that they share some morphosyntactic properties, they share gender, inflection class, derivation family, etc. It can be part of speech, I don't know. And with look alike, what we mean is that they either have similar phonology or similar semantics. And how we define something to be similar phonology or similar semantics will vary a lot, and the ways we do this vary a lot, but this is the core of the idea of analogical classification. As I just mentioned, so in morphology, doing analogical, this type of analogy is basically building a classifier. So if you have a series of items and you have a property of a characteristic, you have to choose for those items, and you have several alternatives, like say gender, then you can use analogical classification to decide what's the gender of a noun, or what's the inflection class of a verb, or etc. Some of the most common domains for analogical classification that have been explored are gender, inflection class, and derivation and family. But you could explore different things, so it's not only these three that are of importance. The way by which we build analogical classifiers varies a lot. The most common one probably is the use of surface rules. This is very common in generative linguistics, although they don't call it analogy, and they probably don't associate what they do with this type of work on analogical classification, but it's essentially the same. And the type of rules are something like nouns which end in a coronal will take the x suffix, and every other noun that doesn't end in a coronal will take the y suffix. That's a surface rule. You can use schemas. Schemas were quite popular during the 80s, mostly with Bybee and Kopek's work. I haven't seen them used that much recently, but the basic idea is that they are patterns. They are not strict rules, they are rather patterns, and if they match, then they apply. And you can say have a pattern like vowel, consonant, T, or something like that. And the most common approach in the type of work I do, and the type of work Olivier does, is to use machine learning or statistical systems. There are many types of statistical models for analogy. Maybe you've heard of logistic regression, that's an option to work with. Maybe you've heard of neural networks, it's also an option. They all have advantages and disadvantages, but you can use any of them. And all of these are analogical relations because all of this capture the basic intuition that if two nouns look alike, or if two items look alike, then they will behave alike. If you're using rules saying that if it ends in a coronal, if you're building things like schemas, or if you're using neural networks, the implementation is very different, but the end result is it's basically the same. Regarding examples, there are many. Here I'm mentioning just a couple, which I think are important to know or interesting to know if you're interested in analogy. Probably the best well-known study was the seminal work by Bybee and Slobin, who looked at schemata in irregular past tense in English. By the time people thought there are regular verbs and they are derived with D or ED in English, and then there are irregular verbs, and those have to be learned by heart. And what Bybee and Slobin did was basically show that irregular verbs in English have a series of different patterns, and most importantly, these patterns are productive. So when they showed speakers of English new verbs, so made up verbs, which fit some of these patterns, then the speakers of English would use the actual irregular conjugation, the irregular form. So what this basically shows is that these patterns are not really irregular, they are just low productivity, but speakers are aware of them. Another very important study was by Köpke and Zubin on German nouns, and what they did was basically to show that German general assignment is not arbitrary. That was the received wisdom at the time, and even now still many linguists believe that German nouns are completely arbitrary in how they are assigned gender. This is not true. Köpke and Zubin basically showed that there are a series of very strong semantic patterns and phonological patterns which help you assign German nouns to their gender. Some of the most famous examples are things like fruits are feminine, and then alcoholic drinks are masculine, and motorcycles are feminine, things like that. But there are also some phonological patterns which help you know the gender of nouns. A very different kind of study, and also very famous, I think, was done by Anne Lappe on ET versus NES in English, which are derivative suffixes for adjectives, and she showed that you can predict very, very well whether an adjective will take ET or NES from their phonology, and that they build basically small clusters of similar words, and they all take basically the same suffix. For this, she used something called AM, which is shorthand for analogical modeling, which is a little bit confusing because this is a very specific kind of statistical model and not something general. It is very specific. I'll talk about it later. There's another study on neutralization in Dutch borrowings. This one's also quite important, by Ernesto Zambayen. A more recent study was done by Bonamy and Tourier, and was on French Ifie versus Issei, and they show that using a very simple logistic regression, they were able to predict with high accuracy whether a base would take Ifie or Issei. Another recent study is on Russian inflection. Basically, in Russian, you have a very large number of inflection classes. Usually people talk about 5, but it's been shown that it's over 80 inflection classes, depending on how you count and what you count and how you look at it. But the point here is that you can predict the inflection class of nouns in Russian from their phonology and their semantics, and that both play a role. And for this study I used a neural network, which is a different kind of statistical model, and the advantage in this case was that to handle the semantics you need a very robust model. But if I had enough time, I could have done it also by hand, by writing just rules and schemas of what's going on. Those are just a couple of examples. I can give you lists and lists and lists and lists of different examples of people doing analogy on different languages and different systems. That's not the point, but in case you're interested. So to summarize this, so far, we can do analogical classification by a vast variety of different means and methods. You can use rules, you can use schemas, you can use statistics, but that doesn't matter. You could rewrite everything using, for example, harmonic grammar tableaus or OT tableaus if you want. And that's of secondary interest. It is interesting to see how different models perform, but the most interesting part is the linguistic part, to understand how linguistic systems work. Now, I'm going to give you two very trivial examples now. First is Sanskrit, which is a real language. And basically in Sanskrit we have either A stems or U stems or E stems or R stems or C stems, which are consonantal stems. Here are here's an example of A stems, kama, desire, and you see there are a series of inflectional markers on the noun, for the singular, for the dual, for the plural. And if you compare with a system noun, vak, voice, you can clearly see that the markers are different. So, for example, for the ablative and the genitive, you have an as marker, which is not directly present in the ablative, and part of a larger marker in the genitive, in the A stem. So these are clearly different inflection classes. You can't possibly claim that this is a phonological process that turns at into as, or it would be very weird. And in Sanskrit, the interesting bit is that these inflection classes are completely and easily predictable from the stem. So if you see an A, then you know it's an A stem. And if you see a consonant, then you know it's a consonant stem. So this is a very simplified view of Sanskrit. I'm ignoring a lot of stuff, but this is an example of how classification works. And this would be a strict rule-based system. So if A then B. Now, to a slightly different seems this is not strictly speaking statistical, but closer to statistical model. Imagine you have the following nouns of two classes, C1 and C2. I should read here C1 and C2. If you want, you can pause the video for a minute and try to figure out what the rule is, or what the rule should be for classifying nouns. Let's say these are nouns, doesn't matter, into genders C1 and C2. So hopefully you arrived at the generalization that if a noun has an A as the first vowel, then it will belong to class C1, and otherwise it will belong to class C2. However, if you look closely at this example, then you will see that this rule is not perfect. So we have these two nouns here, sek and ses or chess. I don't know. I made them up but didn't come up with a phonology and pronunciation. But so if you were to say that the vowel A is associated with class C1, then you would miss three items here. So these three items also have as the first vowel A, but they are of class 2, so that doesn't work well. And you also see that for class 2, the item wak has an A in the first vowel. So unless you build very complicated rules, you're going to miss some nouns. You can capture this model perfectly. But assuming that we agree that this is a reasonable rule, that if the first vowel is A, then it's class 1 and otherwise class 2, then we can evaluate our model. And this is a crucial point in the classification work. This will be familiar to computational linguists, because computational linguists have to evaluate their models all the time. And the most common way of doing it in linguistics is by using a confusion matrix. Confusion matrix basically tells you how many items you predicted correctly and how many items you predicted incorrectly, and to which class you assigned the items you predicted incorrectly. In this case, out of 11 C1 items, we predicted 9 to be C1, so correctly, and 2 to be C2, incorrect. Out of the 13 C2 items, we predicted 1 to be class C1, and we predicted 12 to be class C2, so correct. And from tables like this, we can calculate different accuracy and performance metrics. These are the ones we use most commonly. The accuracy is the most common one, which is just the number of correctly predicted items divided by the total number of items. In this case, it is 0.875. An important baseline of comparison is the non-information rate, and this is basically the proportion of the most common class in the sample. In this case, the most common class has 13 items out of a total of 24 items, and that gives you 0.5417, and this is basically the accuracy a classifier would have if it just predicted the most common class always. So the idea here is that your accuracy should ideally be above the non-information rate. You can also calculate something like confidence intervals or uncertainty intervals for your accuracy. Usually the idea is if you're using frequentist confidence intervals, you say that if the confidence intervals do not include the non-information rate, you can conclude that the accuracy is statistically significantly different from the non-information rate, and otherwise you cannot conclude anything. Otherwise you don't know. Yeah, that's basically the approach. There's also this kappa value, which tells you how much better than random chance your model is performing. This is slightly more complicated to calculate by hand to show you how it's done, but that's the interpretation. And ideally it's going to be high. It goes from 0 to 1, and 1 would mean that the model is perfect. The same with accuracy, but this is so above just random chance. And that's basically all I wanted to talk to you about in this video. There's another couple of videos on a couple of small case studies on analogical classification, different things. You should watch them, and we'll talk tomorrow